What I would like today to talk about is laser-induced breakdown spectroscopy, or we call sometimes laser ablation, assisted with laser-induced fluorescence. For those who doesn't know NRC, so just a few words here. NRC is a federal organization, so we have a budget of more than $1 billion Canadian, and with the support to $270 million for SMEs, and we have over 3,700 employees. And if you add the visitors and the postdocs and others, we have more than 4,000 people. It's the largest organization in Canada. We have a wide variety of disciplines and broad area of services and support to industry from mining to aerospace. We have some areas of R&D's focus, as obviously for any organization. We have four divisions: emerging technologies, transportation, manufacturing, engineering, and life sciences. We have more than 1,400 research centers, and the division of engineering, our research center, as you can see it in yellow here, so it's energy, mining, and environment. It's housed by the engineering division. And in our research center, we have around 200 people, so working on several programs related to energy, mining, and environment. And the laser-based activities, what I developed at NRC, or as I said, or within the division, and it's for those who know Canada, we are located in Boucherville, suburb in Montreal, in the south, as the St. Lawrence River, the south shore of St. Lawrence River. Okay, let us now talk a little bit about the agenda, what we have today. So as you can hear from that, the acronym LA-LIF or LIBS-LIF, I will be talking a little bit about the wording of that and to make it clear for our interaction. First, I will give an overview on LIBS and LIBS-LIF development, since the LIBS-LIF development cannot be separated from LIBS as well. So we have to have a little bit the understanding of that approach. Secondly, I will be talking about the state of the art of the LIBS-LIF technique, and I will be doing some comparison with conventional techniques. I will be talking about analytical challenges and the practical solutions toward that, and not showing only as a fiction science. I will give some examples of real-time analysis of like for contaminants like lead, arsenic, iron, selenium in solid and liquid samples, and also for a few applications as well for like water and weak acid. And I will give some advice for newcomers in the field who will be willing to invest or willing to do something in that field. So I will have some advice to be done, and I will be talking about the LIBS feature, and finally a brief conclusion. So this is the points I will be developing in the next 50 minutes. First, the motivation. Why we use LIBS-LIF? Indeed, like any other technique, there's some driver behind. So in my opinion, the need for real-time analysis to fulfill arising societal needs in mining, manufacturing, environment, food, agriculture, and so on. As an example, World Health Organization has set the minimum contaminant limit, what we call MCL, for most contaminants, and most likely for the health or environmental problems, most likely these traces are in the ppb range. So this is demanding, and laboratory conventional techniques are labor intense and time consuming. It's done in the laboratory, no problem. There is plenty of techniques can do the job. However, there is a lack for techniques that can provide in fast manner and real-time analysis that and give the answer. And when we go to industry, they need to make a decision and taking sample to the lab. It's not a convenient way, and it's time consuming, as I said, and labor intense as well. So it does not respond to those needs. And there's a question as well, sometime where there is some places we cannot have access, and the question is feasible to have a measurement, a standoff measurements. And there are, as I mentioned as well, there are some identified industrial needs for monitoring effluent in mining and applications in refining, like refining metals processing and so on. So everyone who was listening to here, just you know that so the material response to laser matter interaction. So here I will be talking a little bit to define what is the LIBS-LIF and what LA-LIF. Okay, as I said, when you put or you focus a laser beam on a sample, there are many phenomena that it happens, and as you can see, depending on the radius of the laser or the fluence, if we are in a regime like kilowatt by centimeter square, as you can see in the first, I don't know if you can see my arrow here. So it's a laser beam focused. So we have like photothermal process or photochemical or photophysical. And sometimes we have even some like formation of molten material. If you are in a megawatt by centimeter square, you have some vaporization and vapor plume. And we exceed the threshold of ablation, we can have what we call a plasma formation. So the first part here, where we are, and the power is, as I said, in a kilowatt. So in heating or some photothermal processing, this is what is called laser-induced fluorescence. It's very known. You have tons of paper and literature, more than 20,000 papers related to that. I will be not covering this at all. We'll be not talking about, it's not the subject of the presentation. And if we go to the extreme end, I mean, when you have the power or the radius exceeding the gigawatt, exceeding the threshold of ablation or threshold of plasma formation, here we are talking about the LIBS. This is as well, I will be not covering the LIBS by itself, but I will be talking a little bit about it just to understand why we couple that to LIF. So this is here just an idea. So as I said, for the LIF, if you would like, I put here some references here for who's interested. As I said, if you put laser-induced fluorescence in the Scopus, you can get more than 30,000 papers. So here you have a little bit, if you would like to have an idea about this. About acronyms, for those who would like to see what the papers and so on. So for the LIBS side, there are as many acronyms as you can see, but the most common, we put in the red, is laser-induced breakdown spectroscopy. This is the designation of the technique. And there are some people that, as I said, they use this is all acronyms, but there's a little bit, I would say, in the use of them for the moment. Most likely, you can see it's more with the LIBS, as has been accepted as technique, and that the acronym that we use. From the LIF side, there is also many acronyms that we use. The one I mentioned, laser-induced fluorescence, has to be distinguished from what I will be talking, LIBS-LIF or LA-LIF, okay, or LIBS-assisted LIF. I will be using, to be clear, to make it easier, here are the acronyms for what is coming in the presentation. I will be using the LIBS-LIF, most likely, sometime LA-LIF, if it has been mentioned in the slide, that is LIBS-LIF. And as you can see here, there's several acronyms, as I mentioned. Okay, going back now a little bit to understand the things that are related to the LIBS-LIF. Indeed, we have to see it from that angle. So the LIBS is as a vehicle, if you would like, that to make a plasma and generating the plasma from that, make a vapor that we use after that another laser to re-excite the element we would like to analyze. So from the laser matter interaction, if you are in a femtosecond regime, there are several phenomena are happening, and you can see depending on the scale. If you are in a femtosecond range, you have photoionization and so on, avalanche ionization, thermalization, energy transfer, and so on. So as you can see, there are many phenomena here that is happening. So you can see in the reference here, there are many references that can give you a little bit an idea about that. Laser ablation, by definition, it's a removal of material by direct absorption of laser light. So when you focus the laser beam on a sample, irradiation leads to local heating of the material. So we have a heating, we have vaporization, and the plasma is formed. And at the end of the pulse, of laser pulse, we have what we call the emission, that the phase of emission or recombination. That phase here, it's the phase here. This is what is where we use the LIBS here as technique, and we use the emission that comes from it for whether for diagnostics or for chemical analysis. And by the end, we can see some crater here. So at the step 5 here, that is what we can see. You have a mix of atoms, ions, molecules, clusters, particles, and so on. That part here, that we use another laser to excite atoms or molecules or ions which are in that plasma. So here the distinction between the LIF as technique that you can use in the regime that, as I said, in a kilowatt, that you don't have that atomization and you have some molecular analysis. Here indeed you can do elemental analysis and you can do even molecular analysis, but after the plasma is formed. So there's a difference, and from then I prefer using LIBS to distinguish between laser ablation when it's in the vaporization phase. So here we have some atomization here, and that it makes a difference. So I prefer using myself LIBS-LIF, but it's common people they use LA-LIF or LIBS-LIF. So this is, it makes a little bit, it just makes it easier for our understanding. Now I will go a little bit for the from the technical side, or to see what is the LIBS as technique. So for the LIBS side, it's very simple as well. So you need a laser as source of energy to produce the plasma, and the emission of that plasma will give you the chemical composition of the samples. The plasma here is very easy to be generated, but it's very difficult to make useful information from it if you are not familiar with the different science. So here you have the crossroad of different science. You have the laser matter interaction, you have atomic physics, you have analytical chemistry, and you have spectroscopy as well with it. So with that, we have access to the periodic table. With single shot we form here, we have access to the periodic table, and the research around the subject here, as you can see on that screen, we have more than 17,000 papers. It started with the invention of the laser in the 60s. So as I said, I will be not covering the fundamental application of the technique as LIBS, but just some understanding how this, what are the shortcomings of that technology, and why we assist that with the LIF. Okay, so this is here, it makes that. So why we have some interest on LIBS from that perspective? Indeed, the features of the technology have attracted a lot of newcomers lately, but also during the last 4 decades, they have a lot of actions and a lot of attention from the scientific community. And this is basically related to the application potentials of the technology, that we can do some solid analysis, we can do some liquid analysis or aerosols or slurries and so on. And the most important with that we can do online application, not competing with existing technique. The problem with it, that is a limit of detection. We are in a ppm range. So the question is, if we go for environmental applications or for health, so we need, as I said, we need in the trace in a ppb range. So the LIBS is not favorable for that, or not appropriate for if you go to the ppb range. There are some elements in the periodic table we can do it, but basically you cannot do detect element in the ppb range as you do in the lab. And the need here again, that for real-time analysis, and for, as I said, the question for trace analysis. So here I will be not talking a lot about that, but just to give you an idea about the interest that has been there since several decades, as I said. So you can see from the invention of the laser in the 60s, you can see in that here the LIBS paper evolution, and we can distinguish 3-4 periods related to the fundamental side in the 90s. In the 2000s, some applications emerged, and in the last decade we have commercialization phase, and most the big players in analytical chemistry, all of them, they have their toys with the handheld LIBS system. Okay, and again, they have many books as in the last 15 years. You can see here we have more than, as well, about 20 review papers in the same period, and there are also a few books coming. Okay, now, so as I said, to be clear, the need for that is how we can detect traces. And from then, researchers are looking for ways on approaches, like hyphenated approaches, to improve or enhance analytical sensitivity and detection power. So there are several approaches we use. Among them, you can see on this screen, the double pulse mode, or what I put in the red, LIBS-LIF, or RELIBS, or LA, or LA-LIF. Or if we go, what I mean LA is resonant laser ablation, and RELIBS is resonant LIBS. I will be talking about that a little bit later. So there are also resonance enhanced LIBS and nanoparticles enhanced LIBS, and also LIBS here enhanced by microwave or electrical arc. This is what I call hyphenated approaches. Indeed, we have LIBS, and what we do with this mode is to enhance its capabilities to detect or to enhance the LIBS sensitivity. I will be not talking about all of this. Each of them will take about more than an hour. I will be covering a little bit the red, what I put here. I will have a focus on LIBS-LIF as it's the title of the presentation, but the others, and I will be just mentioning a few points what I put in the red here to give an idea. And we have to distinguish two things as well. Here, the approach is called hyphenated, but they're also a combination. There's two things different. Combination is not the use of hyphenated. Hyphenated, indeed, it's, as I said, you have the LIBS site and you use a tool to improve, but it's still LIBS. Here, when we do combination, it's different. Here, we use two techniques. Saying infrared is a technique, or Raman is a technique, and you use it a combination with the LIBS. This is two things different. So Raman, you have access. Your institute or famous with that. So you have access to different analysis, and the LIBS saying Raman give you molecule saying, and LIBS give you elemental analysis. So you combine both. Infrared the same, and the others. When I put here LIBS-LIF as you shown, this is the LIF as the one I didn't talk about. This is when it's in the regime where we use it for molecular analysis. You excite molecules in solid states. It's not the or in a gas saying, but this is give you different analysis than we do here with a LIBS-LIF. Okay, now the approaches to enhance the LIBS sensitivity. There are here several approaches as well. So how we do them, I don't want to go in details, but again, for the audience here or listening, we make a plasma we form a plasma with a laser. With another one in the double pulse mode, we reheat the plasma with the second pulse to extend the lifetime of the plasma, and then we have more photons that goes to our detectors, and we can improve the sensitivity. And there are several approaches. What I will be talking today is the second one here. This we form a plasma, we come with another one to select the trace element we would like to excite, and then we excite it and we see the fluorescence. It's very simple. The other one here, we have a laser approach here that we form the plasma, and another one we call a resonant excitation. Saying you have a matrix, you have saying plasma, aluminum plasma. The resonance, you have the aluminum atoms and has different lines. So we tune the laser to a resonant line of the matrix, of the aluminum, as I said, and then the absorption is related to the major elements in the plasma, and we have better absorption than if you look at the trace. This is here the approach. I will be not talking about again, but just to give you an idea. The fourth one, I will be covering a little bit at the end. This is called resonant laser ablation and coupled to the LIF. And then indeed, in the resonant laser ablation, we have the laser is tuned to the resonant line in the matrix. Okay, so that to form the plasma with it, and with the laser we comes after to excite the trace element we like, or even we can excite the whole plasma, depending on which time you send another laser. We'll see we'll see that a little bit later. Okay, so I will be focusing on the approach 2, and here a little bit the approach 4. That what is, it will be coming in the next 20 or 30 minutes. Okay, so in the LIBS-LIF regime is very simple. As I said, you form your plasma with another one. You come with the laser tuned to the trace element you would like to analyze, and then with that, so you excite and you see the fluorescence. So the advantage of that, so we have a sensitivity in the pp range. I will show you a few examples just to let you know that that is feasible. We have an excellent dynamic range and no spectral interference from the matrix. We have very low absolute limit of detection in attograms, and the system, yes, it has drawbacks we'll see, but it has low cost detection system because we have only the line we would like to see. From then, just small filter enough, and we don't need a spectrometer. The drawbacks that you have to add the laser. Laser by itself is complicated, and you add another one, so it's a little bit here drawbacks from that perspective, and the use of tunable laser as well. What you have, and this is not trivial, and the drawbacks as well that we can analyze one element at a time. So you cannot have a simultaneous multi-elemental analysis. It's just one element at a time. There are some cases we can do that, but it's if I have time, I will show you what the questions. We can see that. Okay, so for the LIBS-LIF, it's not new. Okay, as you can see in the screen here on the slide, it started, in my opinion, the first paper was in 1979, and that quantum measures, and they describe it at that time by hyphenated approach, which is true, and they called here, as you can see in the title, but the name here they call trace analyzer based on laser ablation selectively excited radiation, which is true. Okay, it's true, and the paper here for those who would like to see more. Let us see now the indication for papers. As I mentioned, for the LIF side, there are more than 17,000 papers. For the LIBS-LIF, roughly you can see we have about 250 papers, not a lot. So from that perspective, there is a room here for newcomers, and you can count in your hands. So we have about 10 or 15 papers. There are 4 or 5 groups worldwide working on that. They are like doing some activities in the development LIBS or others, but they are doing that as saying hobbies or saying as curiosity or proof of concept or so on. So this is what it looks like. And we have, as I said, 10, 15 pages. So you can count it in your hands. Okay, now for doing with it as for analytical analysis, what the purpose of using technique. So I'm not going to go with details with this, but just for the audience, so we have here the reference that's in this book edited here. So the message to here, so that we can correlate the LIF signal to the concentration of the element you would like to analyze. So it goes through that, and you have the and that signal. It depends on several parameters. So we have to choose a line that has a great value or a high value of the transition probabilities, as you can see in the formula here, the AUL, and you have 3 other functions. It depends on the interaction between the first laser and the plasma. It depends as well how we excite the element we would like to see, and it depends on the value chain. So value chain for sure, it depends on your spectrometers, the fiber optics if you collect, and the detector you are using. It depends how this is sensitive to the wavelength that you are using. So this is the signal, the message can be correlated to the fluorescence, can be correlated to the concentration of the elements in the sample. And then here, since we have the LIBS as a vehicle to produce the plasma, so the part that is related to the laser matter interaction is important from that perspective. How it's coupled to the samples, how the ablated mass we ablate, and how it's excited for atomization, and how it's contributing to the laser-induced plasma. And then when we do the LIF, so we have that vapor, that atoms here, and how can be covered with a second laser to get the LIF signal. And the most likely as well to be known that we are correlating the signal or LIF signal to the concentration in the solid sample or the gas sample or whatever. So bear in mind that we have the plasma is intermediate between both, and that plasma should be reproducible from shot to shot. And here the challenge and here with some research here too, that plasma should be, as I said, reproducible. It makes sense to correlate the LIF signal to the concentration in the samples. And here we talk about, if take an example, if you have like the stoichiometric ablation is correct or is not correct. If in the plasma the ratio is reflecting what we have in the sample. So that here you can see in the paper here if you would like to see more. But the idea here, this is as I said, when I mean ratio, take an example, if you have copper and you have zinc. So vaporization temperature of the zinc is, it's less than the copper. So it depending on the coupling, if you use a femtosecond laser or a nanosecond laser, UV laser or infrared laser. So the interaction is different from different coupling between the laser and the material. Okay, now for the regime. Here is important. I would like you to focus on that slide here. It makes it easier after that for the remaining of the presentation. So in that slide is very simple. So you can see here that we create the plasma here. That is the signal, the emission from the plasma. We can do as well another laser if the atomization is not correct with the first one. So we can have a double pulse laser that doing the job properly. And then the part here, what we can see, the time after the laser generating the plasma, we have to get rid of the earlier part of the plasma that's not favorable for spectrochemistry. We wait a little bit to have signal to noise ratio better. And then here, this is in the green that you see. This is when you have the light comes from the plasma. And the regime LIBS-LIF, we have to wait a little bit that the excited atom that comes that goes back to the fundamental, and we have a vapor at or atom, like a volume of atoms saying, or ions, whatever, or molecules, that are in the fundamental state. But they are in atoms, they are not in a solid state, they're in the plasma state, but a mix of atoms. And then we send the signal of the laser, we send the excitation laser to do the LIF, and that's what we call here is we select the element we would like to analyze and the wavelength, and then we see. And as you can see here, that is the kind of spectrum we get, and here you see this is a lead line. I will show you this would come from where. So this is here really on even a few ppb here of lead in the sample. So if you see here and you take a window of light and you see it versus time, like a PMT, or like even you integrate the light versus time, that's what you can see. This is a strong continuum. What is comes here, the signal that the LIBS plasma, and when you excite, depending where you are in the time, so you can do, this is what we call the LIF signal, and here in our case, we have to wait to the phase of what we call atomization, where we don't have the plasma. Now, for the choice of which elements or others, this really this atomic physics. So there are some atoms it offers good combination, other they don't offer, or not accessible for the tunable laser we are using. So for the lead, iron, selenium, gold, and so on. This is what have been said in literature. So we have to pick for that the higher values to get better absorption of the laser for excitation, and we have to choose the lines away a little bit preferred. I would use the word preferred to avoid the laser scattering and increase in noises in your signal. Okay, so there are also for molecules as well. We use it for atoms, we use it as well for molecules, and you can see here some literature here for those who are interested to see. And we can see as well that for the LIBS-LIF molecule analysis, so there are also, as you can see in the slide here, and some references showing that. As a setup is very simple as well. So there's many setups. So the way we do, so like to the right, you produce your plasma, and with an OPO that you cover, having a beam to cover the whole plasma, if larger than the plasma, and the beam we send, you cannot make a plasma with it. This is in the kilowatt, even less that what we send it in similar way that we do LIF, and then here we do we excite what we'd like to see, and we collect the light to go to spectrometers, or here another configuration as well, that the vertical, and you have this is horizontal, and you collect the light, that horizontal way perpendicular to the sample. I prefer the light one because not this one, this one here. This is indeed more adapted for industrial application than this one here, because if you are in a conveyor and it varies, so you lose your plasma. And here this is much better. But anyway, this is all, that's some approach that can be done. As a technique now to compare with the others, you have, I said, a bunch of technique in the laboratory. Sorry. So you have a bunch of techniques in the laboratory, as I said, ICP-AS, laser ablation, coupled to mass spectrometry, and others, and the LIBS side. So what should be detection limit? As I said, we have a plenty here in the laboratory, but what we are looking for is, again, for fast analysis, and LIBS-LIF, it offers that approach here. And if we compare to the LIBS, we are in the ppm range. So here it resolves the shortcoming of the LIBS side. And for a preparation, we don't need, you can analyze solid, liquid, gas. We don't need any preparation, and can be used in any atmospheric conditions. No any consumable here. And here, as you see, the others in laboratories, sometimes you need to dissolve the sample as solid, and it's a problem. And if it's a liquid here for ICP is okay. So you have here the yes for this. And when it comes to commercial, all available, but for the LIBS-LIF, there is no commercial system for the moment. So if for real-time analysis, that the way is behind the driver for the LIBS side, yes, and the others cannot be adapted to at all for any real-time analysis or fast analysis. Now I finished the two parts of the presentation. Now I will go to some challenges here and how we can use the LIBS-LIF for analytical work without preparation of the sample. Here, just I put an example here on the side. This is for the liquid analysis. Liquid analysis, as I mentioned, you have to make your plasma, and should be reproducible. That is a message I want you to hear from that. However, the plasma will form. It depends on many parameters. It depends on the, as you can see in the slide here, very simple. So if you foxylase on sample, that you make your plasma here on the surface, it should be, as I said, reproducible. However, what's happening? You have a splash, and you can see you have a vibration on the surface. You have waves, because it's like to throw rocks on the water. You have waves on the surface, and you have formation of aerosols, and you have some bubbling inside. So the plasma formed here, it varies from one. Here you have a plasma between, like you have gas and solid. Here you have aerosols and the liquid. Here you have vibrations, so the fluid is different. Here it's splashing. So the plasma is not the same. So we have to take care of that. So the way, there are many approaches in the literature. So we developed one very simple, and just to take care of that. I will not go into details, but just to let you know that it's feasible, very simple, not resolving the problem, in math or chemometrics. When you have easy problem to be resolved in engineering, do it in engineering before doing the hard work with the others. So you make it very easy after that, and you have make sense when you have a reproducible measurement to make analysis from it. So in that case here, that's we developed a way that here it can be taken care of. So for LIBS-LIF here, so we use the approach as well as I mentioned in the previous slide. And so here we have flowing liquid. The flowing liquid and laminar flow, what it does, it evacuates the bubbles, it evacuates the waves as well, and the exhaust removal, it eliminates the splashing and as well the aerosols. And from then we have surface, laminar flow, and the surface that the laser is like firing. We can make reproducible plasma from that perspective. Okay, as an example, I'll show it to you just clearly, so you can see when you have just the flow, just static, you can see that from shot to shot, you have 200 shots here, so we have 15% from shot to shot. If you have a flowing liquid, you can see to the right here, we have less than 7%. This is shot to shot. If you take an average of 100 shots, so it's a root square, give you divided by 10, so you can have less than 1%, even better than you do in a laboratory without any preparation of the samples. It can be done. This is to show you details of what published already in 2 papers here. Okay, now for the how it works for LIBS-LIF side. Here an example. It's very, very simple. So if you do your measurement, LIBS measurement here, you can see you don't see any LIBS signal and the at all. And if you do the laser just close to the resonant line you would like to on the resonance, so or close, I mean 282, you can see barely you can see something here. But if you are in the resonant line, just you can see the line emerging here. It's very simple, and you can see the noise. There is nothing around. You excite only the element. Why we wait to the end of plasma? I mean the end of the lifetime of the plasma, because you don't have any emission. From then you excite only the element you would like to analyze. You can be very selective. Only the element you would like to analyze. So you can, in the meantime, you increase the signal and reduce the noise. And from then you can improve your sensitivity. So to give you, as I mentioned, so this is here, we wait to the end, and you can see here we have some diagnostics on the plasma. So basically you can see this temperature again from like saying that this is at 1 microsecond. But if you go close to the sample, you can have 50,000 degrees, and then it decreases like this for different fluids. And you can see if you are firing or using the left side after 10 microsecond, so you can see you have temperature below 4,000, which is most likely to be atoms, vapor. That indicates, and that we can have more atoms in the fundamental state than excited, and we improve the sensitivity. How we work? Simple again. So the way to work with it, it's when you have to couple your laser for excitation again to cover the whole plasma, as I said, and you can see when you increase the fluence of the excitation, you can see some increase in the signal. This is here and logarithmic, but after a while you have a kind of saturation regime. Why? It's simple, because if you say you ablate 10 nanograms, and at the beginning you don't have enough energy to cover all of them, say you have 1,000 atoms, and at the beginning you cover 10 or 15 or 100, so you increase your signal up to the way that you excite all the atoms you have in the bottom. So then what we call here is regimes, saturation regime. And in such regime, that here regime we use for LIF is to avoid the fluctuation of the laser or the fluence. For here we are independent from the fluence of the laser. Whatever you use, we have signal independent from that. So if you control the ablation side and you use saturation regime, you can have an excellent reproducibility. So this is and again, for saturation, you can see we have the fluence again, even in the microjoule range by centimeter. So you don't need huge energy. Few microjoule will be more than enough for this. And the details are on the paper here. Okay, so now how we can optimize that? I will not go through all of that. It's just showing a little bit here to you that depending on the delay on interpulses, the message that to be understood from the slide here, 2 things. When you ablate with the laser to make your plasma, you don't control the expansion of that plasma. You control only the laser energy in the environment around. So you can use gas, depending, it dictates the expansion a little bit, depending on the thermal conduction, and also the laser energy that you use in ablation. So you form your plasma, but you cannot stop it at certain distance. It varies in space and time. So when you come with another laser, you have to cover all of this, depending on which time you excite with your laser for the fluorescence. So you encompass a part of that bulk. This is very important, and that coupling is not trivial. And sometimes some laboratories, it took years to couple just only that approach. So the usual way we do, we work at low fluence, so we have we ablate more material, and the material does not goes away from the surface, and then we cover that with the second one, and we have to cover the whole bulk, and then the value chain. Remember, as I said, we depend on laser matter interaction and excitation, and we depend as well on detection. All of three should be optimized for that. And here the signal to give you an idea. So we work like in that case here for the sample using copper here. So we've been working at 11 microsecond here, and the ablation, it was 20 joule by centimeter square as values. Okay, now for an analytical work here, we have as you can see here in the slide. So we have the calibration curve for lead in water using LIBS and LIBS-LIF. So if you are on the LIBS side, as you can see here, the LIBS, it goes here to the right, and the LIBS-LIF, it goes to the left, and you can see clearly that we have the signal, as I mentioned to you, that I showed you. Indeed, it was 0.3 ppm, 300 ppb. That's what I showed you. You see the signal here coming from like 0.3 ppm, 300 ppb, and the limit of detection for the lead, again for the lead yes by LIBS, is around 40 ppm, and with that, when you do for 20 ppm, you go to the limit of detection that goes for the lead, as you can see in the picture here. So we go to almost 40 ppb. So this is in the conditions here again. So we are in like few tenths of joule by centimeter square, and excitation we are in the microjoule. And as I said, this is what it looks from LIBS-LIF. And for the LIBS side, when you are optimized, you have like half a microsecond and 50 microsecond. So the conditions are not the same, but you can see the improvement here, the improvement factor. In the iron, we can improve up to 3 orders of magnitude. If you ask me why the gold here is not, we improve but not much better, is related to the line we are using. And for the gold, it doesn't offer the same. So in the gold line, we have to use the resonant line, and it's a tricky little bit how to overcome the problem, from the scattering of the laser that is coupled with it. So these are some examples to show you here for, as I said, for lead, iron, and gold. So the message to the audience here, that the LIBS-LIF improve the sensitivity of the LIBS, and as the improvement, it varies depending on your choice, but you can have easily, you can get easily 3 orders of magnitude if you are very well optimized. And here there is room as well to improve, but the message here is just to show proof of concept that is feasible. Okay, I will give you here another example from the selenium. Why the selenium here? I'm giving an example. Just it's a case what has importance for the environment and also for mining applications, and also from the analytical point of view, the excitation it's in the UV, and 196 is not the resonant line. They are not saying 300 nanometers or 400 or 250 so on, but here really it's close to the transparency of the air. When it's transparent to this, I think it's when the air is starts to be non-transparent at 185 nanometers for those who will be interested on. Okay, so this is so the setup here is simple. So we like others. So we form the plasma here with the YAG, and you can see the other one. You re-excite and we collect as the others. And again, this is in the laboratory to show you, it's simple as well. So you can see here the cell that for the liquid, and you can see here the OPO here, and the laser that is focused on the samples, and is behind for the detection. And the use we are using, as we irrespective of it as well, but it just as I mentioned, is you don't need, indeed, you can put just a filter. It's good enough because you have only what the selenium line that you would like to see. And again, as existing technique, there's plenty, as I said, for the selenium. You have the ICP, OES, ICP-MS, electrothermal atomizer, and we can get even PPT in the laboratory. And this, they need preparation, pre-concentration, and so on. They use consumable as well. Here, as again, so there is no consumable, and we can do the job properly. Here, what is the calibration curve, as you can see in the screen, and for as a results as well. So we can see that for the LIBS alone, we have a 50 ppm, and if you go for the LIBS-LIF, we are at 50 ppb, and the results are published in the applied spectroscopy for those who would like to see more information. Make a zoom here on site so you can see that we are working at ppb range. This is, again, it's a proof of concept. Okay, again, proof of concept, and this is not fully optimized. We can get even better than this. Even just looking from the side of the detection, we can improve at least 3 or 4, a factor 4, and we can as well from the collection and others. And the number you see here, we can get easily in the ppb, like 1 or 2 ppb range toward that, and that will be fulfilling the conditions or the requirement from the industry or from the World Health Organization, if we are looking for some critical analysis. Here, I will give a few examples, for online analysis based on the LIBS analyzer, to give you an idea that the LIBS-LIF can be coupled to that and provide online analysis. Here, an example that's back, it's about 24 years ago, 25 years ago. That was the first application for online at that time, and the system was monitoring arsenic in industrial effluents. We've been looking for arsenic, and you can see in the slide here this is the LIBS analysis, and what you can see in the dot, this is atomic absorption analysis. So you can see we have a good agreement between both techniques, and we are looking for in a ppm range, so LIBS can deliver the job. If you are looking for the like fraction ppb, so you need to have a hyphenated technique that should be coupled to the LIBS side. Another thing I wanted to highlight here, that the analysis of a study. That why I put the example here. It's just when you are in the study phase, so you have agriculture, you have water. So this is water. It has particles. It's not like clear water that you drink. And that water, it's not slurries, or if you are in the mining industry, you are using slurry phase. So with the LIBS or LIBS-LIF, you can have access to analyze the element, whether in the solid phase or liquid phase. And here, just by way to homogenize the slurries. So with the laser, you can have access to the jet here, solid liquid. As I mentioned, if you have a solid liquid, you have a sedimentation, and with such setup, you can have access to the solid and the liquid. So this is here for the slurry analysis. We have a few samples here. I will not go through them. And here as well, we can go down to the if you would like to do for molten metals, for example. So the approach is you can analyze inside the melt, avoiding the slag on the surface. And you don't need to take sample to the lab from it, and you can do the analysis immediately in the bulk. I don't have a lot of time to arrange for this, I think, but I would just highlight the way as well, not using LIBS-LIF, but using another approach, what's called resonant laser ablation. Use only one laser, only one that is focused on a sample here, and from then you can have access to the multi-elemental analysis. Or you can use it as well if you have a laser tuned to the, if you have lead, for example, matrix as copper and lead. So you can use laser tuned to the trace element as a lead, and with one laser you can have the ablation in the plasma, and the plasma after that can be with the remaining of the pulse. You can excite as well, and and we can do the same. And we have another thing as well, that we can make the plasma with the resonant line to the matrix, and then another example that you can excite all of the elements, and then we can do not only elemental analysis, but we can do multi-element analysis. That here what we call collisional transfer. This is the resonant line and use this. I don't have time to cover all of this, but just here the message to you, it's when we compare LIBS to the LA-LIFs. So just to give you an example, so you can see if you do the LIBS, we are in 40 ppm, but if you do the LIBS or LA-LIFs, so we can have like 0.7 ppm, so you can do better than you do with the LIBS, and this is only with 40 microjoule. This is really appealing. From then, in a small amount, you can be less destructive, but you have better atomization with the coupling between the laser and the sample and the plasma as well. And from then, within that, if you ablate few nanograms, and you see in a ppm range, so your absolute limit of detection will be in the femtograms. This is like you do in mass spectrometry in the laboratory. So you can see here, we can detect in the femtograms and some elements even in the atograms. This is really very appealing and attractive. As a general remarks here for the conclusion, I will cover a little bit here. Just so we have good dynamic range with it rather than the LIBS side, and we can reach saturation regime, which the LIBS signal I mentioned to you, independent from the laser excitation. And this is here we can do as well like atoms, and also we can do molecular analysis, as you can see here. So it's not only for elemental analysis, we can do it also for molecular analysis, and we can go down to depending on the molecule you're using, we can have an excellent limit of detection as well. And the as an instrument, I covered that. The only thing, cons, you need an OPO. An OPO for excitation is a barrier, in my opinion, not in the laboratory. It's barrier for like 24/7 because fragile. If you have one element, it's okay. But if you do a scan for different elements, still for the moment, it's not technology, in my opinion, it's like ready for it. But in the future, I think will be okay. And there are a lot of development, and I'm confident to some extent that, you know, and I can next few years, I would say, we'll see something coming from that perspective. And you know, there is a way to improve from detection side, and this is really improving, and so we can do all of stuff. Now I will highlight in 1 minute here for the newcomers. Indeed, there is a need for real-time analysis for trace element PP range. I show it to you, and I think you are convinced. If you are dealing with geological, dealing with environmental sample or health, you need the PPP range, and there is a need in a fast manner. And there are also room, as you see, 200 papers, not a lot. And when we compare to the tons of others, there are few players in this. So resolve a new challenge, explore new applications, and the advent of new enabling tools, in my opinion, will promise a bright future for reaching new areas not studied yet. And I have here, I wrote a paper recently to spectroscopy, so you have more details about this. You can see it. And I will not cover this. As for the future, just a few words. So there's several, you know, top technologies, and I put it in red here: nanomaterial, solar, and lasers. This is really is a lot of investment on that, and that investment, it needs more from the use of tools, lasers advancing, and from the as well the need for nanomaterials and detection, small particles and nanoparticle range. And I don't find that is not a trivial task, and the LIBS, it offers that. And another things as well I wanted to highlight, this for the industrial, we are witnessing or assisting the fourth industrial revolution, and from then, you know, this is really the sensor side, computers and so on. It needs sensors, it needs real time. Needing real time means this technology I'm talking about, they will have more importance in the future. And as a, you know, the point of views, and not only myself, Lux report showing the sensing side as among the transformational technologies for 2020, which is covered for the 2020-30. And this is a list here, and you can see the sensing. It's very important. And the LIBS-LIF is has to offer in that matter. In the mining sector, there are a bunch of technologies here, and you can see the LIBS in the red, the fluorescence in the red here, and coupling them, this LIBS to LIF, also it has to offer when it needs real-time analysis. And as for the future, there is a regime, as I said, a program regime for nanoparticles. This is a monitoring distribution of elements, and coupled to LIBS coupled to other artificial intelligence as well will offer powerful tool for imaging making decision, and also increase. We will be witnessing or hyphenated systems increase in a system that will have a more sophisticated analysis. And I will not this is okay, an area of focus. I will go to the conclusion. So I hope I give you an overview, fast overview related to the LIBS-LIF as approach and technologies, and I show you the proof of concept of how we use them, and show you some setup for real-time analysis, and I showed you as well how we can detect in the PPB range, and show you as well that we don't need any central preparation or any consumable, that we can do the analysis. I didn't show it to you here, but it's indeed, we are using laser, you know, better than me. So you are using laser, so laser can work at distance. You don't need the physical contact. And then here, I think this is important that the coupling, we can do standoff measurement, so we can go on drones and have a system, you know, as imagination, and you can fire with it and shoot at some areas. And the limit of the PP range has been demonstrated to you, and sensitivity can be improved at least 3 orders of magnitude, which is really appealing. And there's another, we are really working on robustness for online analysis and testing variety of samples. With that, I would like to thank also my colleagues here in the LIBS side, and also we have some students. We do at NRC less academic work, we do more industrial applications, and we are an engineering side. It does not mean NRC doesn't do academic work. No, it's our division. We do more application than fundamental. So we collaborate with universities to develop TRL, and so we have some students working in our laboratories. And I would like to thank as well our colleague at NRS that we collaborate with them with the developed work. And I would like really to thank you very much for your attention, and I exceed my time here. I'm sorry for the organizing committee. I exceed my time by 7 minutes, and thank you very much.